This is another applications video. This is going to be another applications of the equivalence that we've seen between Etale spaces over some topological space T, and sheaves on T, or sheaves of sets on T. So we want to come up with another application of this equivalence. The application we'll see today is an alternative definition of the pullback sheaf. So let me first explain what the pullback sheaf is, and then I'll give the purely sheaf theoretic definition. That's the usual definition. And then I'll sort of say how that construction can be carried out in the Etale space world instead. Let me just say what the value of that is, first of all. The value of that, and you know this if you've seen the pullback construction in the sheaf world, is that the pullback sheaf is a little bit complicated to define, or at least it's complicated to define when it's done over in the sheaf world. But it's actually a pretty natural operation in the Etale space world, because it'll actually just be a real pullback, like an honest-to-God pullback of topological spaces. That's what it'll be over here. So it's hard to define in the sheaf world, but it'll be relatively easy to define in the Etale space world. And that's valuable, right, because we kind of have some nicer way. I mean, it's an important construction, and it's nice to have a relatively clear way of doing it. Okay, so what's the project? So what is this pullback functor? What is the pullback of a sheaf? Well, what's the basic project here? So the project is we're going to start out with some map of topological spaces, some map from a topological space X to a topological space Y. And we're going to have a sheaf on Y. We'll have a sheaf G on Y. This is a sheaf. What we'd like to do is pull the sheaf back onto G. So we'd like to get some pullback sheaf G sitting on top of X. We'd like to take this sheaf, we'd like to start out with this sheaf G sitting on Y and pull it back along F to get this inverse image. I guess inverse image isn't quite the right thing. We want to get the pullback along F of G. That's what this is. F inverse of G. Okay. So how could we do this? What's one way of starting with a sheaf on Y and getting one on X? So here is how this is done in the sheaf world. In the sheaf world, that is in the category of sheaves on our topological spaces. So it's kind of a two-step process. So step one is construct the pre-sheaf that takes U to the direct limit over all V containing F of U of G of V. Just to clarify here, U is going to be an open set on X, and V here is an open set on Y. So we're starting out with this open set U on X, and we're mapping it to this inverse limit of sets G of V, as V ranges over all open sets of Y containing F of U. And well, that's a way of mapping open sets of X into sets, so that's going to be a pre-sheaf. That is going to be a pre-sheaf on X. I haven't said anything about the restriction maps, but that's just common form. So sort of modulo all of that, this is going to be a pre-sheaf on X. Now the problem is that this might not always be a sheaf. This pre-sheaf, which we just defined, this guy, unfortunately, isn't always a sheaf. It may just be a pre-sheaf. So in order to really get the pullback, we're going to define F inverse of G to be the sheafification of that. Is the sheafification of that pre-sheaf. And that's it. That's how we define the pullback of G along F. So I think this construction is a little complicated. First of all, we have to do this direct limit thing, and then we have to do sheafification, which is always a little bit of a black box. So this construction is kind of complicated over this sheaf world, but I claim that it'll be relatively simple over the Etale space world. And I claim, in fact, it's going to be an actual pullback. So claim sort of assuming exactly the same notation as above, the Etale space associated to F inverse of G is this actual honest-to-God pullback that's the way we can do this construction in the Etale space world. So let me say exactly what I mean by this. So what does this mean? What does the claim mean? Well, here's what it means. We started out with a map from X into Y. And then we had a sheaf, G, sitting on top of Y. So let's replace that sheaf G with the associated Etale space. Let's replace it with lambda of G, which will be sitting on top of Y like this, along P. Okay, so this is a diagram in the category of topological spaces, and that category has pullbacks. So we can form the pullback X over Y with lambda of G. And that pullback, we can look at the first projection of that, the projection down onto X, and that'll give us sort of this arrow. What I'm claiming, sort of what we're claiming up here, is that this Etale space is associated to the pullback of F along G. And I guess by associated, I mean something like this. I mean that gamma of X over Y with lambda of G, the sheaf associated to that Etale space, is isomorphic to F inverse of G. Or alternatively, X over Y with lambda of G, that's isomorphic to lambda of F inverse of G. That's what I mean by saying it's the Etale space associated to F inverse of G. And this is the claim that we'll actually kind of prove. So let's start kind of proving this. Well, the first thing we need to know is that this even makes sense. So let me give the lemma and then explain why we need it. So lemma. So let me change all of the letters here. So let's let T going into S with W sitting up here, and I'll call this Q, be a diagram in top, in the category of topological spaces, such that Q is Etale. Well, then the pullback let's call this G, and the pullback of Q along G is Etale. What do I mean by the pullback? I mean, if you started out with that diagram, T going into S, W going into S, and you form the pullback T over S with W, and you looked at this first projection, this map here would be Etale. So if you start out with an Etale space and you pull back, you'll end up with an Etale space. Or rather, the Etale property is preserved under pullback. And the reason why we need this lemma is just to ensure that this claim even makes sense, right? Because if we didn't have that, there's no way we would even know that this is an Etale map. And the lemma tells us that it is. So the claim makes sense. When I say the Etale space associated to f of g is this guy, we have to know that this is Etale. And that's what that lemma just told us. Okay, so what I want to do now is sort of list two lemmas and then very vaguely sketch the proof of this claim. So let's go to the two lemmas. Okay, so lemma 1. Lemma 1. Lemma 1 is something which I've mentioned several times, which is that, well, let's let E going into X of P. I hope you don't mind that I'm reusing some letters here. Be an Etale space. And let's let, oh, I guess I don't have to define gamma for you since we did that in an earlier video. Well, then I can just say gamma of E, the stock of that pre-sheaf at X, is equal to the fiber of P over X. So that's a claim that I've made before, and we'll need it again. So lemma 2 is that, well, let's just assume our usual setup, or the setup that we had before. Let's let this be a map of topological spaces, be a topological map. I just mean a continuous map between topological spaces, and let's let G be a sheaf on Y. Then the stock at X of this pullback is equal to G having its stock taken at f of X. So this identity holds. If you want to take the stock of the pullback sheaf, you just push the point forward and take the stock. So this identity holds. And this is actually not very hard to prove from the usual definition of the pullback sheaf, from this definition. So the claim is not so hard to prove. And that's basically because the sheaf and the pre-sheaf share the same stocks, and it's not so hard to compute what the stock would have to be on this guy over this limit. But anyway, that's lemma 2. Okay, so assuming these two lemmas, I can kind of sketch a proof of the claim. And it's basically just going to be to compare what the two spaces are. So let's compare. Let's compare X over Y, lambda G, with, oh, let me write it out. Let me write it with lambda first, and then we'll see what it is with this guy. So let's compare these two spaces. We'll see that the two spaces are homeomorphic, and that'll be enough. That'll be enough to give the claim. So we want to prove that these two spaces are homeomorphic. Okay. Well, let's sort of translate what this guy is. So by definition, at least on the level of sets, what this is we take all x inside of x, and then we take the stock f inverse of g at x. So let's figure out what this space is. We'll figure out what this space is, and then we'll see how it's going to be isomorphic, homeomorphic to the other space. Okay, so on the level of sets, we have this equality. And now let's use our first lemma. Or let's use the second lemma, then we'll use the first one. So we have this. Okay, maybe I'll just scroll up so we can see both. So this means that this is equal to this. Okay. And how about applying our first lemma, a lemma that tells us that stocks of the sheaf are fibers of the Etale space. So we have these stocks over here. Let's turn them into fibers. This will be P inverse of the stock over the fiber over f of x. Okay. So knowing that, it's not too hard to guess how we're going to define a map from here into here. I mean, what will we do? We'll take some element alpha sitting inside of some specific p inverse of, say, f of x naught, and we're going to map it to the product x naught alpha. So we have this map. Now I'm not going to prove this, but this map is a homeomorphism. This map right here. It's a homeomorphism. If you think about it for a minute, it's not so hard to see that it's injective and surjective. Of course, that's not enough to prove that it's a homeomorphism, but maybe it gives you some hope that it will be. But in any case, I claim this map is a homeomorphism, and since that's a homeomorphism, well, just saying the same thing, that means that this space is homeomorphic to this space. So this space and this space are homeomorphic. And that tells us that gamma of x over y with lambda of g is isomorphic to gamma of lambda of f inverse of g. Right? If these two spaces are homeomorphic, then when we hit them with gamma, we'll get things which are still homeomorphic. And because of a fact which we proved in an earlier video, or probably not proved, but at least mentioned, this is isomorphic to just the pullback of f along g. We can cancel out the gamma and lambda when we have some sheaf over here. So we have that this guy is isomorphic to this guy. And we're done. So this was an alternative construction of the pullback sheaf. And at least, once you've gone to the trouble of defining Etale spaces, I think this is a somewhat more natural construction. I think that this construction of taking actual pullbacks of topological spaces is a bit more natural than this definition, the one that we started with. Now, to be fair, that kind of naturality comes at a price because defining Etale spaces is a pain. But once you've kind of gone through that work, I think that this definition is a little bit more intuitive. Okay, that's it.